Well, many thanks to the organizers for inviting me to give this lecture and to honor the memory of Jean-Marie Souriau, but as you know, also we are celebrating 50 years of La structure des systèmes dynamiques, which was a very important book for many of us. So this is, it was difficult to find an original title for this. As you will see, my lecture, it will be mainly historical. And therefore I felt that probably the right way of doing it. So what I want to speak about is, of course, my own interaction with Jean-Marie Souriau, although I was at some distance, but I will tell you why it was important for me. Also, I want to talk about the book, because we're also celebrating 50 years of this book, La structure des systèmes dynamiques. Again, at a very peculiar moment for mechanics in France in particular. I will then focus my lecture on really something which has been really very, very important for the development of symplectic geometry, which is the approach proposed by Joseph-Louis de Lagrange in a series of memoirs, but in particular, of course, his Mécanique analytique in the late 18th century. And as you know, the very key new element was the birth of symplectic geometry. For good, through the introduction of the space of elliptic motions. So, my interactions with Jean-Marie Souriau, actually, of course, when the book appeared, immediately I realized that this was really a very special thing, because maybe something I should tell you, I was at that time just getting out of École Polytechnique, after we struggled, a number of students, with courses in mechanics which we couldn't understand. They were fundamentally wrong, and so as students who want to understand, we just read all possible books we could find on mechanics. So we read Sedoff, we read Truesdale, we read a number of French authors also. But of course, when the Souriau's book appeared, it was fantastic to have something which was bringing a completely different vision. So that was my first encounter. And then several times, I had the opportunity, since I visited Marseille a few times, to also interact with him or attend conferences in Aix and various opportunities to exchange, in particular, not only on symplectic geometry, but also on really his conception of the role of mathematics. I will make some quotes on this, but also his interest for the philosophy of science and what is relation between abstract ideas and concrete formulations, which I think was definitely very penetrating and quite original. Actually, I should even say singular. One thing which was very singular, as you all know, if you have read his books, is, of course, he made a point in using the terminology that nobody was using. So this is even pointed in some of the remarks on his books that provided you use a good dictionary, then you are okay with most what he says. But of course, the key point is the content, which was very original, with a real vision, and in many ways. It's interesting to note that his book on relativity actually appeared before the other one, but although I was personally interested in relativity, I didn't relate to it until quite late. So it's kind of a surprise. I don't know why, but I should, of course, have looked at this book earlier. In particular, because during my time at École Polytechnique, we had a seminar on general relativity, which was organized by the students, nobody else. And we tried to get as much information as we could. So that was one of the reasons why later on I also connected to Jean-Marie Souriau was definitely this, his interest and contributions to general relativity and my own personal interest and in general relativity later on. Actually, maybe one thing I should say is also my first intention when I left École Polytechnique was to do mechanics, because I felt I was not good enough to do mathematics, so I would do mechanics. But then I couldn't find anybody in Paris who would accept me as a student, for the reason that I came with my own project for a PhD. And this was, although it was after '68, it was unthinkable that a student could come up with his own project for a PhD. Anyway, So I turned away from mechanics and went to differential geometry, which was the closest field, and that's the way I met Marcel Berger, who had been a fantastic advisor later on. So in a sense, I've been diverted from mechanics to differential geometry, but then, of course, always keeping in mind how important mechanics was for the development of geometry altogether. So one thing I want to show is, of course, we all know that his contribution, Jean-Marie Souriau's contribution, has been very, very broad. Here I'm quoting what were the final remarks by André Lichnowitz at this very important meeting in 1990 in Aix-en-Provence, at the moment where Jean-Marie Souriau retired. So here is what André Lichnowitz said at that time as concluding remarks. What is remarkable in him is that he's the only one of us who could legitimately belong to 4 international scientific unions, mathematics, of course, but also mechanics, physics, and astronomy, and everywhere as a true professional. Actually, as I will comment in a minute, you could even add, of course, philosophy of science, and as was said, the people who support this conference are also philosophers. So anyway, I think that's an interesting quote. And also that's something which is taken away from one of his, Leitfaden in one of his book, which is how you connect the whole physics, the whole theory of the world, with also all kinds of mathematics in a very intricate way, which also shows that for him, all these things were very truly, deeply connected. And so I like this diagram very much. To explain it takes about a full course for a few months, but of course that's one of his it shows really his vision of science and the connection between mathematics, theoretical physics, mechanics, and so on. The other point I wanted to mention was also his connection to the philosophy of science. And this is one taken from the introduction. I will comment on this introduction from Structure des systèmes dynamiques. And here is what he says. The direct consideration of an abstract space of movements that he calls U shows that what one could call the paradox of the physicist, namely this one who doesn't create a world out of nothing, thinks that he has to care about real facts. And, but the evolution of any material system, as complex as it is only represented by one point in this manifold U, which is the abstract space of movements. The other points are of a purely virtual existence, and still it's only by structuring the set of all these virtualities that the physicist can, in a certain way, explain and also actually anticipate what the real will be doing, what the real world will be doing. So I think it's one example. Of course, one can take many of his approach to things. That is how he thought that abstract thinking can contribute to the theory of the world, in particular to physics, and which I think is quite interesting because he comes back to this a number of times in some of his publications. Another one that I would like to mention, of course, one of his remarkable latest book is so-called Grammaire de la Nature, Grammar of Nature, in which I will take from this book, which is very interesting to read, 2 quotes. One I like very much, which is, shoes are a tool to walk, mathematics a tool to think. One can definitely walk without shoes, but one doesn't get very far, which I like very much as a quote. Of course, as a mathematician, I feel comfortable. Maybe if I was not a mathematician, maybe I would not feel so comfortable. It doesn't say that the other sciences are not tools to think. I mean, it just says that mathematics is one of the tools to think. And another quote I wanted to show also from Grammar of Nature is mathematics pose a somewhat more delicate question. What makes them think that, them being the mathematicians, what makes them think that their object is universal? The object of mathematics is mathematical truth. But what is the criteria for mathematical truth? nothing else but the sovereign decision by the community of mathematicians, which I think is very interesting. I completely share this view about this subjectivity which is in mathematics from that point of view. That is, the community has to agree what is acceptable as an evidence because it's built and checked and constructed. And last, and therefore the mathematical scene is singularized among the various scenes of science. That's only people who really play the role of object, which is this interaction between the people who create the discipline and the discipline itself, which really, I think, is a very interesting point from the epistemological viewpoint. So these are just two excerpts. Of course, the whole book is worth being quoted, but of course, I don't have time to do that here. So that was these were just in a snapshot elements I want to take from contribution from Jean-Marie Souriau. Of course, I will develop more about his contribution to symplectic geometry, which I took as the title of my lecture. But I wanted also to point to this other dimension, which to me is extremely important in the philosophy of science. So I'm coming to the book, La structure des systèmes dynamiques, as I told you. We are celebrating this year 50 years, which is a good time. And actually, when it came out, I think it was some kind of a revolution. It was, as I will say, it was something was happening in the world on such issues. And as I already hinted to, at this time, mechanics was taught in a very classical way, both at the École Polytechnique at the university, I must say. And personally, as I mentioned already, a number of students were unhappy about the teaching we had. And therefore, we organized our own seminar without professors, just to learn about what could be another approach to mechanics. And it was very, very stimulating. It was just before May '68, so that was the spirit of students. Before demonstrating, people wanted to do science by themselves, which, of course, as you know, is the best way to learn the discipline, just if you work by yourself. And so this was something it was not a large group of people, maybe 20 out of 300, but that was enough to have a very lively seminar and to read many different books. And in particular, one thing which we found very frustrating is that the mathematical content of the courses we were exposed to was very limited and sometimes even incorrect. So it was something we didn't feel comfortable about, so we wanted to cure that. So, as I was mentioning, there were at the same time similar books coming out. One, of course, which had been very important was the book by Abraham and Marsden, which I think the first edition is 1967, so about the same time. A second edition, which has been quite expanded and with contribution by Tudoratiu, appeared in 1978. But of course, the first edition, because it also connected, it took a quite different point of view, less philosophical, much more connected to the theory of dynamical systems, which at that time was really exploding, and with the work of many people, in particular Steve Smale, but many others, Pugh and Schub and so on. So this book, of course, was a book I'm in the context I described to you, I immediately jumped into and looked at. Another one which was very important, although we had access late on, I couldn't find the exact date of the Russian edition, which I think is the very early 70s, but I couldn't find the date. But I know some people actually gave me some translation they had made of this the book by Arnold. They did, I mean, before it appeared in the French edition in 1976, which also was another very interesting. It's interesting also to compare the styles, because the styles are quite different. And as you know, Arnold was somebody who definitely was very much put back by the Bourbaki style, and even very aggressive towards the mathematics of Bourbaki. And you know, Jean-Marie Souriau was also turned away from mathematics by Bourguignon, as he mentions in some interviews he made about his own trajectory when he left École Normale. He felt that Bourguignon was too much present. It was not the way he wanted to look at things. So just to show that this book, which really played a very important role, was also happening at the moment where a number of people were feeling that the literature, which is of course extremely rich on, on mechanics, in particular on analytic mechanics, people felt there was something missing, in particular its connection to the most recent development in mathematics. And so if you have looked at the book, I mean, the book starts with a very long chapter, I think it's more than 50 pages, which is called Introduction, which is it's rare that a book has an introduction of so many pages to start with. And of course, very central to this introduction is the seminal work of Joseph-Louis Lagrange. And so here I'm quoting something that which is in the book, in the introduction, La mécanique analytique de Lagrange. So the mécanique analytique of Lagrange, published at the end of the 18th century, is a piece of work which is not complete, as certain chapters are only esquisses. This is why one knows about the mécanique analytique of Lagrange through the works of others, Poisson, Hamilton, Jacobi, who really contributed to fix its form. Actually, later, if you read more what the introduction was, what Souriau says in introduction, for him, of course, the work of Lagrange, in particular, one specific conclusion of a very intense period of 3 years, published in 1811, played a very important role. And for him, it gave the final form. Except in terms of the names, Lagrange is, of course, very much associated to mécanique analytique, but the later developments have been more or less put under the table. In particular, Poisson is much better known than Lagrange for this. And also what is interesting, if you have the opportunity to look at the exchanges between Laplace and Lagrange, and clearly Laplace doesn't get what Lagrange tries to explain to him. It's very interesting to see this. And so the point that a little later in the book Jean-Marie Souriau makes is that analytic mechanics is not an old-fashioned theory, but it appears that some of the categories which are traditionally attributed to it have become outdated. And among them he speaks about space of configuration spaces and a number of notions like this, because he wants to substitute to them some other concept, which of course are exactly the heart of the whole book, which is in particular the spaces of motions and things like this. So this was one, so this is really the strategy, and of course the strong statements that you can find in the book are like this one, which is also interesting in style. Usually you don't find this in books of this sort. Since it's more a question of opinion as of physics, we will simply renounce to evoke the notion of configuration space. And we will see later that we are not losing anything by doing that, which is quite a strong statement, because all the books in mechanics at that time were all based on configuration spaces. And so he says further, it's quite clear that the laws of physics can be discovered by comparing observations and experiences, which allows to deal with the various aspects, partial aspects of the real as different virtualities. So again, we have this balance between reality and virtuality, which appears in this. So, as you know, the heart of the book is symplectic geometry, which is, because that's what he says a bit later, in the case of a dynamical system, which is really the evolution of a mechanical system, we will suppose that the virtual is composed of the space of movements, and that the structure of the space of movements is symplectic. Its isomorphisms, symplectomorphisms, can be deduced easily. And then he later on discusses that, of course, this group of symplectomorphism is infinite dimensional, because there are many. It's very easy to generate a number of them. And of course, the comments he made that some finite dimensional subgroups of this group of simple ectomorphism are very, very important. And that's what he called a dynamical group. And then he says the dynamic group being given, the set of dynamic variables which are constructed from this dynamical group can be organized in a geometric object that we will call moment. And of course, there were already mechanics in the notion of moment, but his approach is much more fruitful, much more general, and in particular related very, very clearly to an action of a group, and a group in the sense, a group of the type that he's considering. So I think this is one of his very important contributions, which is to give a very broad understanding of notion of moment, both as a mathematical concept and at the physical or mechanical concept. And then some new viewpoints, which I already started to discuss, which is the following one, which of course was for me as a mathematician quite surprising, because at that time I was just learning about cohomology, is the cohomology of the Galilei group allows to associate to every dynamical system a number which is independent of the movement, which can be interpreted as the mass of the system. So to see the mass appearing as a cohomology class is kind of an interesting feature, which of course is, very much Souriau's-like in this spirit. And of course, the other point, which is very important, because at that time, sometimes classical mechanics and relativistic mechanics were considered as different worlds, which had no points of connection. And in his case, he insists that one can go easily from classical mechanics to relativistic mechanics just by replacing the Galilei group by the Poincaré group, which is the two groups of invariants of the two theories, and then by knowing how one embeds into the other, then of course you get this extension in a very efficient way. So just to give you how the book was perceived, I want to quote two reviews which I found quite interesting about the book. Actually, they were not reviews immediately published, but it's interesting that the first quote I'm going to make is a review by Shlomo Sternberg in 1980, so quite later. But he was discussing the Abraham Marsden second edition, that is 1978 edition. And then, of course, in a quite substantial review, he also lists of a few other books which are really important in his view. And he mentioned Souriau's. So Souriau is a deep, and so it should be Souriau's in a sense, but he writes, Souriau is a deep and original book. At every turn, one finds novel, profound insights into the relation between geometry and physics, not only in mechanics, but also in statistical mechanics and quantum mechanics. It has already had a major impact on portions of the mathematical community. One hopes that it will have a similar influence on physicists. So I like that, because definitely Shlomo Sternberg was focused on some other things, but he, in passing, just says what he thinks of the contribution of Souriau. He also discusses a few other, in particular another one by Thirring, which was also a very interesting contribution to field theory at that time, starting from classical mechanics. The other one is really a review of by Ivalo Mladenov of the English translation of the book by Souriau. As you know, there have been a long, long time before the book was translated. Maybe some of you know why, but I don't know why, but I'm sure you can comment. Which, as you know, the translation was done many years later, and with a subtitle, which is a symplectic view of physics, which I think is quite appropriate. And here is what Mladenov says. Now, what makes of course, it's a long review, but now what makes the book under review so special in this context? First, it introduces some new notions, that the space of motions, the orbit manifold. Of course, it's not a new notion. It was in Lagrange already, but of a dynamical system. The momentum map, a unifying concept for the constants of motion. The situation here is reminiscent of the Klein view on geometry, which linked a notion of a geometry and the group of invariants of a geometry. the mechanics is determined by the Lie group, which preserved the symplectic structure. So these were just two examples of reviews of the book, which I think were quite interesting in their the fact that they identify what they consider the key elements. Of course, they say much more. They are much longer reviews. So I'm finishing my comments on the book. I actually, as you will see later on, I want to concentrate on this new approach by Joseph-Louis de Lagrange, and partly to say that I think it's in the history of mathematics. It's really I'm talking about the 1808 paper, which is the first of a series, because I think this paper was definitely a turning point in the history of mathematics. Maybe I will come back to this slightly later. So, of course, the starting point is Newton's Principia, in which he was able to recreate the Kepler's laws in a deductive fashion, which was quite remarkable. So you know this extraordinary book. In the sense that it was very, very important for mechanics altogether. The first time the law of the basic fundamental law of mechanics was stated in a correct way using acceleration, and also at the same time in the same book he also proposes the law for gravitational interaction, which of course is very, very important. And from that on he finds the Kepler's law. So the Kepler's law, of course, as you know, show that elliptic trajectories, which are the motion of a planet around the Earth, for example, are solutions of the differential equation of motion, second-order differential equation. And then with the peculiarity that these elliptic trajectories, the sun, or actually the center of gravity of the system, is the focus, one of the foci of the ellipse. Of course, if you have a planet and the sun, the difference of masses makes it that the center of gravity of the sun and center of gravity of the system is not very different. So therefore, you can think that the sun is really the focus. And then, of course, that's a very interesting picture that you find in Newton, for example, explaining how you get about these ellipses. And I must say that this description is very interesting to look at. Of course, so this is very classical, and of course the difficulty with the solar system is that it's not just one planet like the Earth and the Sun, but there are other planets. So you have many more, and therefore the other planets are perturbating. If you are interested in this two-body problem, that is the Sun and take the Earth, for example, the other planets are also interfering. And the approach which had been taken from this was that because of the value of the masses of the planets compared to the mass of the Sun, of course you can try to look at this as perturbations, and try to look at expansion of the motion from the exact solution, which is a nice ellipse. So you have to get perturbation from this ellipse. And of course, many people after Newton did that quite successfully with quite good approximations. But some very basic questions were not resolved. For example, is it possible that one of the planets get out of the solar system? This remained undecided, and therefore people were looking for other techniques to do that. And so, as I said, this was very successful. But then the more you want to get into this theory of perturbations, the more the calculations become really extremely involved and extremely complicated. And so Lagrange really looked at the whole question of the dynamic in a different way, and therefore he really made a major step with his mécanique analytique, which it's interesting to see that mécanique is written with an H and analytic with no Y, but that's the way the book appeared, and which is a very remarkable book in the sense that it contains really many totally new insights. In particular, the key feature, which I think is not so often stressed, But I personally feel it's an absolutely major achievement. Of course, Newton's achievement was to understand that acceleration is the key at the heart of mechanics. But of course, you can do that if you are in a vector space, but if you are in a linear space. But as soon as you are in a non-linear space, what is the meaning of acceleration? Because in a sense, if you're in a non-linear space, if your space is smooth enough, you can talk about tangent vectors. But actually, the acceleration is not a tangent vector, so it's an object of second order. And therefore, how do you make it an object of first order, which you can compare with vectors? And of course, this is the whole point of you need one more data, which is typically a Lagrangian, and then from the Lagrangian you can get to the Lagrange equation, which is just the nonlinear version of the acceleration. And so this is a really major achievement, very cleverly done. And actually, if you look now at really at the truly intrinsic formulation of this, you have to wait a long, long time. And I think the first person who did that was actually Joseph Klein from Grenoble, who is the first one to really give completely intrinsic formulation for this, which is a bit painful, but actually, if you really want to understand things for good, I think that's the most unavoidable. And so, as I said in the book, which I referred to, Souriau really puts the main emphasis on the conclusive list of 3 major contributions by Lagrange, which summarize several articles by Lagrange in this period, 1808-1811. Lagrange was not the only one to contribute, as I will mention in a minute, because Denis Poisson was also contributing quite substantially. And so, personally, I want to concentrate on the 1808 article, because I think from the point of view, from the epistemological point of view, it already contains the whole story. Of course, if you really want to look at the solution of the problem he was considering, the next articles are also very, very important. By the way, I should really mention that this sequence of articles and the environment has been studied by several authors. Patrick really dedicated a sequence of articles called Lagrange et Poisson sur la variation des constantes. So Lagrange and Poisson, the variation of constants, in 1998, and Charles-Michel Marle really with a very substantial article on the inception of symplectic geometry, the works of Lagrange and Poisson exactly during the same period. So you can read the many detailed account. So my point is really to stress that already the 1808 article contains really the key ideas, and but there are many others. But this period has been extraordinary. Let me come back to something which I want to relate to, because it's very interesting. This period of the end of the 18th century, beginning of 19th century for geometry was also the end of uniqueness of Euclidean geometry, because at the same time you had really the fact that, discovery that there were non-Euclidean geometries, but geometry in the sense of the typical name of the word, namely measuring the earth. That is, geometries which have to do with length, when, of course, this geometry, which is symplectic geometry, has to do with the measure of two-dimensional surfaces, which is a very different object. And so it's very interesting to see that this very period, more or less between 1780 and 1820, was a period during which geometry went from just one concept, Euclidean geometry, which had been resisting for 2,000 years, and to something which actually it was understood that there are many different ways of doing geometry. And of course, later on, there was also the generalization by Riemann, which was very, very important. But at the same time, the birth of symplectic geometry as a new way of looking at spaces and structuring spaces. It's remarkable that this happened in this very exciting moment. Also, politically, the period was not also uninteresting with first of all, the end of the 18th century with the l'encyclopédie and all work of really what is very often called the Enlightenment period, but also the French Revolution and also a lot of turmoil in the European politics. anyway, so that's, this period has been really so extraordinary that it's really worth being looked into. So here is the mémoire I want to refer to, which is a mémoire sur la théorie des variations des éléments des planètes, et en particulier des variations des grands axes de leurs orbites. So the very small subtitle, of course, is very important because in this memoir, Lagrange wants to discuss the possibility for a planet to get out of the solar system, and of course, having the large axis of the ellipse just blowing up. So that's really his concern. And so, as I said, it was, I think, no, maybe you don't see the date, but the date is 22nd of August, 1808, I think. So here is what it says. So that's the very beginning of the article, of the memoir. So just recalling some things which are well known is that if you want to look at orbits of a planet, you have a number of parameters to really identify the orbit, which are really the major axis of the ellipse, its eccentricity, and then of course you have to fix. I will come back to this in a minute. How the ellipse sits in the three-dimensional space, because all the rest was to describe the ellipse in a plane. And of course, since you are interested in the position of the planet, it's not only the orbit that you want to add, but you want to know where on the orbit it is. So that's what is called l'époque, so in a sense, the date. And so these 6 parameters are really the parameters that really are of interest to people who are looking at this situation. And so when he says the last century, it really meant the 18th century, because that's 1808, the beginning of the 19th century. He says that people have, of course, used differential calculus, as Newton taught people, to solve these problems. And so, of course, with the basic law that the motion of a planet, which is attracted by the sun, and the law is, of course, the inverse square of the distance. And you have these, in three-dimensional space, 3 second-order differential equations, and that you have to integrate. So second order, so you have 3 equations, so you have 6 constants of integration that you need. And so these are the 6 arbitrary constants that he's referring to. And then comes the question, which I already mentioned, that, of course, if you are interested in the Earth and the Sun, of course, there are other planets which are really also perturbating the whole system. And therefore, it just explains that, of course, when one is forced to look at approximations, that it look at all these actions of the other planets on the system. And so here is now the very critical place, which I think is remarkably explained, which is so therefore, if you look at the elements, the 6 parameters of an elliptic motion, which if the sun was alone would be constants, you would be on a fixed ellipse, then because of the presence of the other planets, the motion is not anymore elliptic. The ellipse is perturbated. But then the key remark is to say, one can still say, can consider it as elliptic at any time, which means that it is a variable ellipse, and the ellipse you are considering is oscillating to the true trajectory of the planet. So this is where comes the translation into a completely new approach, which is to say that instead of looking at the problem in normal space, which is, of course, three-dimensional space, plus the extension by velocities, you have a second-order differential equation. So the 6 parameters, which are the 3 positions, the 3 variables for the position, and then the 3 variables for the speed. Then you transpose it to another 6-dimensional space, which is the space of elliptic motions. And you think of course, if there were no other planet, the motion would be stupid. It would just be at an elliptical motion. But then, because of the presence of the others, you will be moving in the space of elliptic motions, which is this, the comment made there. Of course, if you just have this, you don't do much. But then later on, that's what I will explain, which is completely explained by Lagrange, actually he discovers that this space of elliptic motions actually mathematically has a very interesting structure, which allows to rewrite the equation you're used to in a completely different way. But then, of course, it comes naturally endowed with a symplectic structure, which of course didn't exist at all at this time, and is just cooking up the whole thing. So this very specific passage is quite remarkable. So he says that actually he has already considered this implicitly, because that corresponds to in his theory of the variation of constants that he has introduced for differential equations in general. And then he says that he had a series of papers. But in these papers, if you look at them, you will see that actually he has not really built a geometric image, which there is really built to say to go from this six-dimensional space to another one, and in this other one to realize that it has a structure, when for the other one it was just a pure direct calculation without understanding what is the geometry which is underlying it. And so, so now he explains what is the purpose of the memoir, which I already actually announced, which is to expose new formulas, which I found on looking at the variations of the elements of the planet, and also in particular because he's very interested in this possibility of a planet escaping application to variations of a major axis, and also to develop the analysis which led me to that. And you should think of analysis as being what today one would call geometry. That is the fact that there is a structure underlying it. And he says, well, as a side comment, this looks like it's worth being looked at by geometers, but be careful that the word geometers just means mathematicians at that time. It doesn't mean anything had to do with geometry, because it has some uniformity, some generality. In particular, because he made immediately the comment that, of course, he's dealing with this question in the context of celestial mechanics, where, of course, in the case of planets which are captured around a star, of course, the elliptical orbits, but also there could be some non-elliptical orbits. But, of course, more than that, he says that it applies with the same success to any other assumption of gravitation in which orbits could be any other thing but conic section. So what he says in particular is that actually he has understood that the fact that on the space of motions you have naturally endowed symplectic structure, he completely understands it. And actually the calculation he does is very, shows that he has understood that fully. So I think I find this really, this paragraph and the one before, really quite extraordinary. So just maybe to come back and to look back at this notion of the space of elliptic motions, to be pedagogic in case some of you have never been exposed to this, let me come back to something which actually historically was quite extraordinary, was the fact that you see the introduction of coordinates, which today are just so obvious, was not at all evident, because for a long time in mathematics, really geometry and numbers were really separate worlds. There were a few bridges, but no systematic bridge. And the person who really introduced that was Descartes. Maybe you don't know, but there is an appendix to Le Discours de la Méthode, which is called Geometry. Here is this appendix. And in this first page, really there is he explains how the calculus of arithmetics really can be related to operations of geometry, even in a comment in the margin on top of that. And it's very interesting to read the comments by Hermann Weyl, for example, on this. Hermann Weyl says that this statement here was an act of violence. That's Hermann Weyl's words. Because really, for a long time, because of the Pythagorean belief that anything which was irrational was unbearable. So, of course, because as soon as you do geometry, the diagonal of the square with length 1 is square root 2, so it cannot be put back in the world of numbers. That's totally unacceptable. And therefore, this really was a big change. And from that on, of course, what one calls analytic geometry was possible. So the idea of having parameters to space, to really having parameters to look at the the study of a certain space was also done by Euler in the famous Euler angles. So what is the purpose of this is, of course, to get parameters on the group of rotations, of three-dimensional rotations, which, of course, was a very important contribution by Euler. And so you have these famous three Euler angles with how you construct them. If you look at, of course, the way you study rotation is take three vectors forming an orthogonal basis, and you look at how this orthogonal basis is transformed, and the Euler angles allow you to really follow this transformation. So these are these local parameters, and of course this of course was, in a sense, maybe you should think of this, although I tend to claim that the space of motion is the first abstract space created in mathematics. You can think of this maybe as a first attempt, because for the first time you could look at the group of rotations or the rotations in three-dimensional space as also an abstract space, although it's less abstract than the space of motions, of course. And anyway, so in the case of celestial mechanics, of course, the objects you are interested in are ellipses. So the first thing to look at are ellipses in R3. The first thing to look at is to look at ellipses in the plane. So there are clearly three parameters for the ellipses in the plane, as I was suggesting: the length of the major axis, the eccentricity, and the angle of the major axis with a fixed direction. So with this, you can completely construct an ellipse in the plane. And of course, we are looking at the situation in three parameters. So you need, of course, this further position that you need. So of course, one has to do with how do you identify a plane compared to some other fixed plane of reference. And the last one, which is the angle, corresponds to the epoch that is along the ellipse. You have to tell where you are. So these are the six-dimensional space, which I'm copying again the slide I showed you, which was the very beginning of the article by Lagrange, in which he explained these six parameters. And of course, now the key point is the discovery by Lagrange, which is quite remarkable, because also he understood how general that was, that the space of elliptic motion in R3 comes equipped with a new type of structure that he's describing in the rest of the article. So the way he does it is today looks a bit tedious, complicated, but you should remember that for all of us, of course, the simplest example of a symplectic setting is the cotangent bundle of a manifold. But of course, this is not the way it appeared. It appeared in much more subtle way in this context with the space of elliptic motions. So he's really discussing, he starts from the differential equations and really he knows how one gets integrals. And but then he says, of course, we have now the perturbation. So that was the previous equation in the case where there is just two bodies, so it's very simple. And you have the six constants corresponding to integrating these differential equations. And so now when you have the perturbation, then he said in particular that he will use the technique of variation of arbitrary constants. In particular, he quotes the exact place where he has done that. And of course, at that time, it's a pure analytical trick. There is no structure in it. It's pure calculation. Of course, very clever calculation, but that's just what it is. And so the key point, of course, is he just look at a certain elliptic expression of the coordinates and of the differential. But then anything which used to be the constants, now you will think of them as really variable. And therefore you come up now with this, you have to look at the differential, which are corresponding to this variation of constants. And therefore you have to look at this new, way of looking at things where you have the usual differential, and then the differential coming from the fact that they are variation of constant, that they are perturbations. And so he just introduces the very key element, which is the quantity omega, which is supposed to measure the perturbation. And then he just writes all the equations which are how the variation of arbitrary constants are related to the various equations. So when you do that, you end up having a number of equations, and he said, well, from this I don't know what to do, except he makes the comment, fortunately, I could find a combination of these equations which leads to very simple and very remarkable result, and this is what he explains. And of course, the key thing is to introduce the anti-symmetric structure, which he calls the quantity now. Before that, they were called with little Roman letters, but now they are written with capital Roman letters, which of course are these skew-symmetric quantities mixing the various things. And therefore, he even introduces this symbol, which are the XAB and the XAC, XAF, and therefore he will represent the various quantities, just because you can replace the various quantities. And then the big discovery, which is of course fundamental for the whole discussion, is that with respect to the variable x, if you look at the BA bracket, then it's the opposite of the AB bracket, which of course and so of course he does that with the x, but he does that with the other one, and then he can really, at the end, one finds further equations, and he has a full description on how the parameters vary. And of course, the key element is the final formula, which of course allows you to give a full description. He wrote them in the form of differentials. Of course, you could also divide by dt and really look at the variation of various parameters. And so the very key element is this function omega is a function of the usual variables, but the presence of this quantity is only through this formula, which tells you how omega is varying. So, so therefore, he can really conclude that he can really study the variation with introducing the various perturbation. And so for him, what is very critical is these values can really satisfy equations which are differentiating according to this variation of constants, which is this delta. And so he just rewrite the equation in a certain form, and then you end up really having, that's the last one, which is really the element, which is the various expression that you can form. And of course, you try to eliminate anything which contains the time, and therefore you end up being able to have a description of the evolution using exactly these brackets that he has introduced. So I think it's very interesting, so that he gets in the end general formulas, which I think you have to be careful that there is an equal sign which is not properly copied at the very beginning. So the key point, and that's more or less his conclusion, is that it's quite remarkable that the various partial differential derivative of omega relative to the arbitrary constant can be expressed as differential function of this same constant without that the time enters. It follows that one can also express the various differentials as partial differentials from the function omega relative to the other one, multiplied by simple function of these quantities without the time. Then one has only to deduce the values of these differentials from 6 preceding equations by the ordinary methods of elimination. And we will see that they will all have the form that we expect, where the very critical feature is the fact that the coefficient capital A, capital B, and so on can be given just by the coefficients, which are these brackets that he has introduced, and will be, as a consequence, simple functions of the elements without t. So this brings a very important theorem and extremely important for the theory of evolution of planet. And so now he says that he can go further, not just do that. And for example, he's looking at the major axis. And so as he said before, goes back to 1780. He has shown that its differential can be expressed as a different partial differential with respect to omega, or derivative with respect to time, and therefore he just deduces from this that in the end he gets the formula that he wanted to have. So I think this was this. I mean, one has to look at the whole text to see that really already the 1808 paper, from the point of view of the concepts, all the concepts are there. Of course, today we prefer to have another approach, which is much more axiomatic and setting up the symplectic form much more upfront, which actually came up somewhat later, but in a very useful way. Thank you very much.